Hi and welcome to problem 4.4. So by this point, you've probably already noticed, also by means of problem 4.3, that a lot of the results in the book are actually presented through the exercises, right? So number one, it's important to do the exercises, and number two, it's also a really good idea to gather the results you get from the exercises and keep them in some kind of formula collection or just have them in your notes, just so that you don't only focus on the results you get from the rest of the book. So in problem 4.4, we are asked to show a result that is actually rather useful. So what do they ask us to do? Here we let x be x1 comma x2. So now we're considering bivariate distribution. So we're going to consider the simultaneous distribution of x1 and x2, which then has the density fx. And they say assume that we can write this density as g1 of x1 multiplied by g2 of x2 for two non-negative functions, g1 and g2. So what does this mean? This means assume that the simultaneous density of x1 and x2 can be split up into a product of two expressions, where one expression only depends on x1 and the other expression only depends on x2. So that's essentially what they ask us to assume. So assume that the density, so assume that the simultaneous density can be split up into the product of two expressions, where the first only depends on x1, and the second only depends on x2. So, and the second only depends on x2. Then show that, so assuming this, our goal is to show that x1 and x2 are independent, which we may write up as such. So to show that x1 and x2 are independent. So what does it mean for x1 and x2 to be independent? Well, we already know that x1 and x2 have densities, so let f x1 of x1 denote, you know what, instead I guess I'll just write f1 because that's quicker to write. So let f1 denote the density for x1, denote the density for x1, and let f2 denote the density for x2. Then we know that by definition of independence, x1 and x2 are independent if and only if the marginal density of x1 multiplied by the marginal density for x2 is equal to the simultaneous density fx of x1 comma x2 for all x1 and x2 in R. So what do we actually have to show? Well, we want to show that x1 and x2 are independent. So we want to show this. So show this. This is what we want to show. And what we know is this thing up here. So what we know is actually that the density can be written as the product of g1 and g2 for two functions g1 and g2. So we actually can see that what we want to show is we want to show the simultaneous density can be written as the product of the two marginal densities. And what we already have assumed is that the simultaneous density can be written as the product of two functions where one depends on x1 and the other depends on x2. So our question is, well, aren't we almost already there? Because we want to show that this is true, and we know that this is true. So it is assumed that there exist g1 and g2 non-negative such that f x of x1 comma x2 is equal to g1 of x1 multiplied by g2 of x2, right? And we want to show I don't know why that's in one word. We want to show that x1 and x2 are independent. So we want to show that the simultaneous density is written as the product of the marginal densities. Hence, we are done if we can show that g1 multiplied by g2 is equal to f1 multiplied by f2, right? Because we know that g1 multiplied by g2 is the simultaneous density, and we need to show that the simultaneous density is equal to this. So we are done if we can show that g1 of x1 multiplied by g2 of x2 is equal to f1 of x1 multiplied by f2 of x2 for all x1 and x2 in the reals. Okay, so if you've followed up till now, then actually when you then start doing these calculations, then probably you've already been able to do this exercise, actually. So just take a little break and try and see if you can do the exercise yourself if you haven't done it yet. And in the next video, I will show you guys the solution.